This is the second lecture in topic 2 of your summer assignment. So this is topic 2, part 2, atomic structure. As usual, please make sure that you've used this to create your own learning targets. A lot of this you'll find is review. So as we're working, I'm going to do a little bit of examples and try to bump it up just a little bit to the AP level. But definitely you should have a good foundation on your own. This lecture will not be comprehensive. So if you've made your own notes, you're ready to go ahead and add to them as you watch the lecture. If not, please come back here and do that first. Okay, so atomic structure at the AP level is something that they just kind of expect that you know. So it should be really easy for you to look at a periodic table and determine the number of protons from the atomic number, determine that the number of electrons is the same or not, depending on if it's an ion or an atom, and then determining the number of neutrons only from being given a mass number, not from using the average atomic mass on the periodic table. So by now you should already have this information of the atomic nuclide symbol in your notes, that when we write this A to Z notation, sometimes is what it's called, the mass number is on the top left, which would be the number of protons plus the number of neutrons. Remember that the number of protons is the same as the atomic number. And so the bottom part of this, the Z number, would be the atomic number. And if it's a neutral atom, we don't include a charge. Sometimes you'll see it with a little 0 here to show you that that charge is neutral, but most often we don't include a charge unless it's an ion. And then you'll see the electric charge here. This is a kind of a weird example because sulfur doesn't usually make a 1+ ion, but this kind of gives you the idea of how that would work. Okay, so I'm not going to focus on ions in here because this is largely about atomic structure, but I'm going to do a few examples with you so that you can work through this. You will need a periodic table, and I didn't put one in here, so I'm going to go back to, this is asking about titanium, so I'm going to go back to the periodic table that I have here, and we're going to find titanium, and we're going to see titanium is right here with an atomic number of 22. So when we're looking at this, then I need to picture that titanium symbol should be 22 and then whatever the mass number is. Okay, so each atom, all of these atoms of titanium would have the number of protons would be 22. And since they're all atoms, none of them have charges, then the number of electrons is also 22. And then to find the number of neutrons for all of these different isotopes, what I can see then would be for this one, it would be 46 as the mass number minus 22 protons would give me 24 neutrons. And this one then would be 47 minus 22, which is 25 neutrons, etc. I'm not going to do all of those with you. The way that College Board might ask you to use this in a question is not this straightforward. Rather, they may give you something that looks like this and ask you which of these are isotopes of each other, and maybe have something like this. Right? And so you'd have to recognize that isotopes of each other have to have the same, they have to be the same element. So they have to have the same atomic number, but different masses. And this is because isotopes are different by the number of neutrons. So definitely be on the lookout for how College Board will use this. I also have for you a question that's asking you to identify these elements. And so remember that to identify these elements, we're going to do this from the atomic number. So when I look this up for Q, atomic number 5 would be the number of protons. And since these are all neutral, for this would also be the number of electrons. And the atom with 5 protons is boron. I can look at that from the periodic table to see that. Whoops, sorry. From the periodic table to see that. That the atom with 5 protons is boron. Remember, we're basing that on atomic number. And then the number of neutrons would be, I can't see it anymore, mass number minus atomic number, so number of neutrons in this case would be 11 minus 5, which is 6. Okay. For part B, Now we have 41 over 20, so the number of protons equals the number of electrons, and in this case is 20. 20 protons is calcium, and the number of neutrons would be 41 minus 20, which is 21 neutrons. Okay, so you can see how this works. Go ahead and try part C on your own. Stop the video here, and then come back and check your answer. Stop the video. Okay, so you should, for part C, have obtained that this is the number of protons is 53, the number of electrons is 53, and the number of neutrons is 131 minus 53, which is 78. Okay, based on the number of protons, this is an atom of iodine. So hopefully you got that right. And if not, please continue to work at that. This is something that College Board just kind of assumes you know by now. Okay, so I do want to talk a little bit about relative atomic mass, because this is something that we kind of do quickly in first year chemistry that you may not really have understood why. So please remember that the atomic mass unit, which is our relative to other atoms atomic mass descriptor, now is also called the Daltons. I think this is funny because this is something that your book says that I've never seen before. So now you can win Jeopardy by knowing that an atomic mass unit is the same as a Dalton. Okay, but what happens is that 1 AMU is basically the mass of one of the nucleons in the nucleus of an atom. So the nucleons are the particles that are in the nucleus, which from what you know now about atomic structure would be a proton or a neutron. So a nucleon is a proton or a neutron. And for the most part, their mass is pretty much equivalent. Neutrons are slightly heavier than protons because technically a neutron is composed of a proton and an electron. But because electrons are so small, pretty much we always talk about a proton having 1 AMU and a neutron having a mass of 1 AMU. This really comes from the definition that 1 AMU is 1/12 of a carbon atom. It has to be a carbon 12 atom, so it has to have 6 protons and 6 neutrons. Okay, so this was a random decision. It could have been any element, but carbon is pretty much the most prevalent element on Earth. And so carbon 12 itself is the most abundant isotope, and most carbon is carbon 12. So this is where they created that relative mass. So really what we're saying is if I have a mass of an atom of helium-4, that it has a mass equal to 4/12 of a carbon 12 atom. So this is our AMU system. Okay, the other thing that I wanted to talk about is mass spectrometry. This is new for you. Mass spectrometers, I hope that you watched the video, that you read the part in your book, and that you watched this video. If you did not watch this video, go back to the learning targets and watch that before you continue to finish this lecture, because I think that will be a really important way for you to understand what happens. I'm not going to explain it in this lecture, but I am going to talk about the graph or the plot that comes out of a mass spectrometer. So this is how we separate different isotopes of an element, or different even molecules of a compound, etc., into their constituent parts. Okay, so we get this plot that gives us a percent abundance and a mass. Okay, and so we're doing this for they have to be in gas form, so we have to make them ions, etc. But we're doing this for neon, and we discover 3 separate neon isotopes, and the mass spectrometer gives us their percent abundance. So remember that the formula for average atomic mass is the percent abundance of the isotope times the mass of the isotope plus the percent abundance of the isotope times the mass of the isotope for as many isotopes as you have. If you leave this percent as a percent number, like 20% or 30% as 20 or 30, then you have to divide this by 100. But I typically will make this, instead of the percent, I'll make it the decimal of the percent first because I like the math easier. So if it's 30%, I make that 0.0, etc. Doesn't matter which way you do it, just pick one way and make sure that you are consistent. So I'm going to set this up in this question because it asks you to use the data from the mass spectrometer. So the average mass of neon would be 90% or 0.9048 of neon 20, and they tell you in the question that neon 20 really isn't really 20 AMUs. It's very close to that. So we're going to multiply that by 19.99244 AMUs, and then we're going to take the percent of 0.27% and make that 0.0027. This is for neon 21 times neon 21's mass of 20.99385 AMU. And we're going to add to that the percent abundance of neon 22, which is 9.25% or 0.0925 times neon 22's mass of 21.99139 AMU. And then I'm going to do this math and crunch it out and discover that I get 20.18004668 as my answer from my calculator. Something that you need to know about average mass is that we want this to look like it came from the same piece of equipment. So if this is how many decimal places you have in your AMUs of what you're given, then you're going to keep the same. So I see 5 decimal places. Remember that taking an average is really an addition operation. Dividing by the percent abundance, dividing by the sample size is just to create an average. So I'm going to keep 20.18005 AMUs as the average mass of neon. Okay. So this is also something that College Board doesn't really ask you to calculate this way. They might make this a multiple choice question and ask you to choose what the average mass of this would be, in which case you'd be saying most of these isotopes are neon 20. So I would expect the average to be slightly higher than 20, but not a lot because the percent abundances of the other 2 isotopes are very small. Okay, so this is exactly what I see when I do the calculation. All right, the other way that they do this is not as common anymore, but they used to do this all the time, where they asked you to know that the average mass was given to you on the periodic table and to find the percent abundances of 2 isotopes of an element. Okay, so in this question, they gave you the actual mass of the 2 isotopes of boron. And if this were a College Board question, they would not have given you the average atomic mass. They would have expected you to know to look it up off the periodic table. So this is really important that you know that the average mass is on the periodic table, or you would not be able to solve this problem. The other thing that they expect you to know is that if you have only 2 isotopes, they together have to add up to 100%, or if you're going to make it the decimal, they together have to add up to 1. So the way that I set this up, I'll show you the setup and the answer, and I'll ask you to crunch the numbers and make sure that you really get what you're supposed to get. The way that I set this up was that the average from the periodic table was 10.81. I had the first isotope as a percent abundance of X, and its mass was 10.0129 AMUs. And the second isotope has a mass of 1 minus X. You could make this 100 minus X, but then remember you have to take the whole right side of this over 100, and then you'd have to cross multiply the 100 by the 10.81. So this is the reason I like to make them the decimal form. So remember your 2% have to add to 1, and rather than adding to 100 if you use the decimal form. And then the mass of the second isotope is 11.0093 AMU. And now this becomes finished with the chemistry, just do algebra. So I'm going to ask you to pause the video here, crunch the numbers, and see if you can solve for X. Okay, so you should have solved for X at this point, and you should have gotten that X was 0.2000, which then translates to 20.00% of whichever isotope X was attached to, which is the 10.0129. So this would be the boron 10. And then to solve for the second isotope, I'm going to do 1 minus X, which is then 1 minus 0.2 which is then 0.8000, which is 80.00% of the other isotope, which was boron 11. Okay, so hopefully you were able to do the algebra successfully. Like I said before, really understanding this is the chemistry and the rest of it is algebra. Okay, the last thing that I want to talk about is average mass from mass spectrometry here is, this is the question that's in the tools section of this chapter. And so I do want you to know that this graph that's here was not a part of the question. I posted the graph so that you could see what's happening. So what we can see here is they wanted to know how many peaks would be in the mass spectrum of chlorine with its two naturally occurring isotopes, okay? And they tell you it occurs as two atom or as a diatomic molecule. They also tell you that in the mass spectrum from the mass spectrometer, you're going to see peaks for the molecules and for the separated atoms. Okay, so what we see here when they ask for how many peaks is 5. And you can see the 5 peaks in this because this isn't a part of the answer that I'm giving you, but I want you to recognize that you have a peak here for the single atom of chlorine 35, and you have a peak here for the single atom of chlorine 37, the two individual atomic isotopes. But then we have these other 3 peaks that are really heavy and must come from the molecule. So now it becomes kind of like a logic problem. You have a molecule of 2 chlorines, and it could be made of these 2 chlorine. It could be made both atoms of chlorine 37, or it could be made from 1 atom of chlorine 35 and 1 atom of chlorine 37. Okay, notice that this peak right here is much higher. This is the one that corresponds to a mass of 70, which would be the mass of 2 chlorine 35s. 74 is this really small little peak, and then 72 is in between. Okay, so notice that the heaviest and lightest particles, the lightest particle would be the individual chlorine atom, and then the heaviest particle would be the one from, whoops, sorry, not that one, the one from the 2 37s together in a molecule. Notice something. The percent abundance of the Cl35 is 76%, and you can see that here. So it's going to be much more likely that if you have 2 atoms of chlorine together in a molecule, they are both chlorine 35. And since it's 24% abundance chlorine 37, it's much less likely that they would be both chlorine 37. So this is kind of an interesting way to see how that mass spectrometer's spectrum that's provided to you can give you some information. You can do this for compounds as well, and in organic chemistry you will do this, but not as a part of this course. When we use it in this course, we use it simply for elements. So I hope that you learned something new today and that you were able to add to your previously made learning target notes, and I will see you next time.